This lecture will serve as an introduction to the topic of carbohydrates, the last topic we'll be studying in this course. Unlike some of the other organic structures we've studied this quarter, you're probably already somewhat familiar with the term carbohydrate. For instance, we've earlier talked about functional groups like amines or aldehydes, and you may or may not have heard those terms prior to this class. But inevitably, you've heard the word carbohydrate before. So let's start by talking about the origin of this term. Carbohydrate, like the name implies, literally means hydrates of carbon. And this term came about because when the first scientists started studying these molecules, they noticed that the ratio of carbon to hydrogen and oxygen in the molecules suggested that each carbon might be attached to one water molecule. That's because there was always twice as much hydrogen as oxygen. So the ratio was for every one carbon, there were 2 hydrogens and 1 oxygen, which naturally makes you think of water, or H2O. In reality, we know that carbohydrates, while they do have that ratio of their atoms, don't actually have H2O anywhere in their structures. What carbohydrates really are polyhydroxyaldehydes and polyhydroxyketones. So these molecules, when we look at them in their simplest forms, will have either an aldehyde functional group or the ketone functional group. All carbohydrates also contain many different OH groups, the alcohol functional group. So, as we'll see to a limited extent, carbohydrate molecules can often undergo the same reactions as aldehydes, ketones, and alcohols. Now, there's a wide variety in carbohydrate structures. We'll start by looking at the simplest carbohydrates, and in fact, that's all we'll focus on for this particular lecture. So these carbohydrates will seem very simple. In fact, their organic structures won't be any more complex than what we've seen earlier in the quarter. As we'll see in our next lecture, however, carbohydrates can also be extremely complex molecules, basically because they can start out with simple building blocks to become very long and complex structures. So let's talk about the simplest carbohydrates. The simplest type of carbohydrates are what are called monosaccharides. It literally means single sugar, and for that reason monosaccharides are sometimes referred to as simple sugars because they're basically the simplest form of carbohydrate that exists. Monosaccharides vary in their individual structures, but in general they have between 3 to 7 carbon atoms. Now we can name them, generally speaking, based on these simple facts. Although the naming is somewhat different from the IUPAC naming we've seen previously. Aldehydes, for instance, are usually classified as aldoses. The OSE ending just indicates that they're a sugar, and the ALD is meant to indicate that they have the aldehyde functional group. Similarly, if you have a monosaccharide with the ketone functional group, it can be referred to as a ketose. Furthermore, if you'd like to be more specific, you can also add to these general terms an extra bit of information that specifies how many carbon atoms are present. For instance, if I was dealing with the simplest monosaccharides, I'd be dealing with something that had 3 carbons. So I would use the term tri, and I would have their names as either aldotriose or ketotriose, depending on the structure. When dealing with 4 carbons, I could look at an aldotetrose, the TETR coming from the term tetra, or 4, or I could have a ketotetrose. Notice that we're not using the IUPAC alkane naming of BUT for something like butane. For 5 carbons, however, we go back to the same prefixes we've become familiar with in IUPAC names. A 5-carbon monosaccharide could be classified as either an aldopentose or a ketopentose, depending on which functional group is present. 6 carbons would be an aldohexose or a ketohexose, and the 7-carbon monosaccharides can be classified as aldoheptoses or ketoheptoses. Again, these are just general terms because they tell us about the functional group that's present and potentially how many carbon atoms are present. They do not, however, give us individual structures. In order to know what the actual structure is, we have to have more information. Generally, monosaccharides, or for the purpose of your notebook you might just write MS, have a structure that's fairly straightforward. As we mentioned, they contain either an aldehyde or a ketone functional group and then a number of OHs. The number of OH groups that are present depends on the number of carbons, because generally there will be one OH for each carbon. Now there's an asterisk here for a specific reason. There is not an OH group on the carbonyl carbon of the aldehyde or ketone functional group. So for example, in a monosaccharide that had 5 carbons, like an aldopentose or ketopentose, one of those carbons would be the carbonyl carbon. Each of the other 4 carbons would contain exactly one OH group. The simplest sugar that exists is an aldotriose called glyceraldehyde. And glyceraldehyde looks like this structurally. Again, notice that we have an aldehyde functional group, we have a chain of carbons, and each of the carbons, with the exception of the carbonyl carbon, has exactly one OH group attached to it. Now there's something else we have to consider about all monosaccharides, and that is their chirality. Based on what we learned in our previous lecture, take a moment and consider this molecule and ask yourself, how many chiral carbons are in this molecule? That can actually be a little bit difficult to do with the line structure, so I'll go ahead and change this into a complete structure, even with its 3-dimensional details. Now take a second, pause the video if you need to, and decide how many chiral carbons are in the glyceraldehyde molecule. As we learned in our previous lecture on chirality, one of the easiest ways to determine if a molecule is chiral is to locate chiral centers, which in organic chemistry are most commonly tetrahedral carbons that have 4 different R groups. In this molecule, there is only one carbon which is chiral, and it's this carbon here. This carbon is tetrahedral because it has 4 single bonds. One of the bonds goes to the carbonyl carbon. A second bond goes to a carbon with 2 H's and 1 OH. One of the bonds goes to a single hydrogen and the other goes to an OH group. So because each of those bonds is bonded to something totally different from the other bonds, this is a chiral carbon. And as we learned in our previous lecture, that means that this will have an enantiomer, a non-superimposable mirror image. As is true for most monosaccharides, including glyceraldehyde, we're going to see the presence of 1 or more chiral carbons. And when I say most, I mean pretty much all monosaccharides that you could possibly need to know about for this or your upcoming classes. So, this is an example of a molecule that has a chiral carbon, which means that when we picture it in 3 dimensions, if we were to try to superimpose it on its mirror image, it wouldn't work. Now, as we also learned in our previous lecture on chirality, that can be a little bit hard to do if you're just visualizing these models. We can physically make a model, but again, that's not always the most efficient thing to do. If you were able to do this in your head, what you'd notice is if I take the model on the left and I try to turn it around and superimpose it on the model of the right, watch what happens to this. As I turn this molecule around so that the carbonyl bond is in the right place, this, which points to the front on the left-hand version, would actually be back here, pointing to the back on the right-handed version. So these are enantiomers because they're non-superimposable mirror images. And as we already know, that means that these 2 molecules may have very different physiological effects, especially somewhere like the human body. So this is one of the first problems we run into with monosaccharides, is that even though they're relatively simple structures, I mean they are called simple sugars after all, they do have chirality, so it's important for us to be able to visualize them in 3 dimensions, and line structures are not always the best way to do that. For this reason, we have a special type of structure that we like to use when we're dealing with monosaccharides. It's called a Fischer projection, or just a Fischer structure. Fischer projections, or Fischer structures, are a really simple way to depict molecules that have many chiral carbons, and in particular, we always use them when dealing with monosaccharides. When we deal with something like glyceraldehyde, yes, you can absolutely draw a line structure of it, and yes, you could absolutely draw an expanded complete structure. But putting it into what's called a Fischer projection allows all scientists to quickly look at the molecule and instantly know some really important 3-dimensional information about it. So let me show you how to take a typical structure and turn it into a Fischer projection. The first thing you want to do is rotate the molecule so that the carbonyl carbon is towards the top of the screen. In the case of an aldehyde, that means that the aldehyde functional group will be at the top of the molecule. In the case of a ketone, it won't be at the very top of the molecule, but we orient the molecule so that the ketone group is as close to the top as possible. Now, this three-dimensional information may seem a little bit jumbled, but really what we're doing now is we're looking down on the top of the model. And notice that this means some of the bonds are pointing towards you and some of the bonds are pointing away from you. We can show that using dashed lines and darkened lines, or we can actually see it in a model. But what a Fischer projection does is it makes all of that information intrinsic in the structure. So here's how we make a Fischer projection. As I said, make sure the aldehyde or ketone functional group is as close to the top of the molecule as possible. And while it's not totally required, we tend to draw the carbonyl bond pointing towards the right. Now you can always draw out the complete structure of the aldehyde, but remember you may also see it in its condensed form as CHO. As some of you learned in the section on aldehydes, sometimes that condensed form is a little more trouble than it's worth, but you will see it in some places. Now that I've situated that aldehyde group, or if I had a ketone group towards the top, what I'm going to do is extend the bond from the carbon down through the rest of the molecule. This line now represents my carbon backbone. And notice I'm not doing a zigzag to indicate the carbons. What I'm going to do first is finish the molecule by locating the last carbon. Now the last carbon in all monosaccharides is always going to be bonded to 2 hydrogens and 1 OH group. Furthermore, this is not a chiral carbon. So for that reason, I don't have any reason to draw it out in more complex structure. Instead, we usually write it in a condensed form as CH2OH. So now I've taken care of the aldehyde functional group and I've taken care of the last carbon in the molecule. Now I'm ready to draw in any remaining carbons. In glyceraldehyde, which is what we're looking at now, we only have one other carbon because it's the simplest monosaccharide that exists. So what I'll do is I'll draw a line across the carbon backbone. That line forms an intersection that has perfect right angles. It basically makes a T or a cross. That cross represents a chiral carbon. So if I see just one place where I have an X or a cross in a Fischer projection, I only have one chiral carbon. But as we'll see in an example in a moment, if I see more of these intersections, I know I have more than one chiral carbon. Now, all I have to do is put on the remaining atoms, which are the H and the OH. This is where orientation is very important. In this case, I have the OH pointing to the right. That means the OH is actually coming towards you if we were to look at it in 3 dimensions. So I put the OH on one side of the T and the H on the other. This is the complete Fischer projection for glyceraldehyde. Again, it's not that much more simple than just drawing a line structure, but it's valuable for 2 reasons. One is, as these monosaccharides get more complex, these will sometimes be much easier to draw than line structures. But there's another reason why Fischer projections are so important. Here's the reason. Fischer projections, because they have such a very particular orientation, they allow us to instantly determine whether we're looking at a molecule that's in the D form or the L form. In other words, which enantiomer we're working with. And it's incredibly simple once you have a Fischer projection to do this. All you have to do on any Fischer projection, no matter how big or small, is locate the lowest chiral carbon. That basically means find the X that's closest to the bottom of the molecule. In this case, I only have one chiral carbon, so it's even easier. Once I've located that chiral carbon, what I'm going to look at is which direction the OH points in. Literally, which way is it drawn on the page. In this case, my OH is pointing to the right of the structure. That fact tells me that I'm actually looking at D-glyceraldehyde. If it was pointing in the other direction, meaning everything else about the Fischer projection was the same, but this OH group was actually pointing to the left, then I'd be dealing with L-glyceraldehyde. So this is the other major advantage of Fischer projections, is simply by drawing a molecule in this particular arrangement, we no longer have to do anything complex to determine if we have enantiomers and which enantiomer we're looking at. Instead, we just have to make a quick determination of whether we have the D or the L form. Let's try an example. The structure of the monosaccharide glucose is shown below. It's already drawn as a Fischer projection. First, tell me in general, is glucose a aldose or is it a ketose? And is it a ketopentose or is it an aldotriose? Give it a general classification. Pause the video if you like. Glucose is an example of an aldohexose. I can tell that because it has an aldehyde functional group as opposed to a ketone, and it contains a total of 6 carbons. So I would call it an aldohexose. Now, is this glucose molecule in the D or the L configuration? Remember, all we have to do to make this determination is to go locate the last chiral carbon on the bottom of the molecule and determine which way the OH group is pointing. On the bottom of this molecule, I find my last chiral carbon and I see that the OH group is pointing to the right. So because this OH group points to the right, I'm dealing with the D form of glucose. This would be called D-glucose, and this is the type of glucose that's actually in your bloodstream. We'll see it again in a second. Let's try one more example though. Draw the Fischer projection of L-glucose. Now remember, the orientation of the OH groups is of paramount importance because it really tells us which of the saccharides we're looking at. So how can I draw the mirror image of this molecule so that I have L-glucose instead of D-glucose? Pause the video and give it a try. To draw the Fischer projection of L-glucose, I'll start by drawing the same backbone structure that all Fischer projections have. Furthermore, since glucose is an aldohexose, I have my aldehyde group at the top and I need a total of 6 carbons. 2 of them are already represented in the aldehyde group and the CH2OH group towards the bottom of the molecule. Now here's the other important factor to consider. Notice that the pattern of OH groups in glucose is that we only have one group that points opposite the other ones. In other words, the second OH from the top has to point in the opposite direction. Now for L-glucose, I need to make sure that the OH on the bottom points to the left. So to follow this same pattern, I get a mirror image. My OHs are exactly opposite the pattern that I have in D-glucose. This would be the structure of L-glucose in a Fischer projection. Now, glucose and glyceraldehyde are just 2 of many different monosaccharides, and I'm not going to require you to memorize all of these. In fact, the only one I want you to be able to draw from memory is the one we just did, glucose, because it is so important biochemically. However, there are many other monosaccharides that are out there, and we'll see a few of them in this and the next section. We just saw glucose, and as I mentioned, D-glucose, which is one of the enantiomers of glucose, is the version that's in the human body. For this reason, it's also called dextrose. Dextrose literally means D-glucose, and dextrose or D-glucose is also known as blood sugar because this is the type of sugar that we use in the human body. Now there are other types of sugar out there that we can take into the human body and use, but many times that's because it's broken down into simpler forms, and many times one of those forms is D-glucose. Another example of a monosaccharide that can be metabolized in the human body is D-galactose. D-galactose is actually part of the lactose structure, which you may know lactose as being milk sugar. Look at how similar D-glucose and D-galactose are to each other structurally. These are both monosaccharides, and they're both examples of aldohexoses because they contain 6 carbons and an aldehyde functional group. Really, the only structural difference between D-glucose and D-galactose has to do with the arrangement of the OHs, and this is true for most monosaccharides. Simply by switching the position of one OH group, in this case the one that's third from the top of the molecule, changes glucose into galactose or vice versa. Now, that means that these are 2 totally different structures, and they act differently when placed in the human body. Now let me show you one more example of a monosaccharide, and this time I'm going to show you a ketose. Specifically, this is actually a ketohexose because it contains the ketone functional group and 6 carbons. Specifically, this ketohexose is D-ribose. It's a sugar named ribose, and we're looking at the D version. You may have heard of ribose before because it's an important part of deoxyribonucleic acid, better known as DNA. In fact, deoxyribonucleic acid is basically built from ribose that's lost one of its OH groups, hence the term deoxy. Now, it's not a coincidence that all three of the monosaccharides you're looking at are in their D form. That's because in the human body, pretty much all monosaccharides and carbohydrates come from the D versions of those molecules. As we learned about when we studied chirality for the first time, the L version of a monosaccharide generally has a totally different physiological effect, if any, than the D version. That's different than proteins, which are built from amino acids that usually come from the L version of the molecule. Now, all three of these structures are the Fischer projection form of the molecules. And while Fischer projections are relatively easy to draw and extremely easy to interpret, they don't actually represent the true three-dimensional structure of the molecules in the human body. So for instance, if we really could see at the molecular level in your bloodstream, we would look at D-glucose and we wouldn't see this long carbon backbone. The reason for this is that for most monosaccharides, there's a far more stable form they can exist in than just a long, stretched out, open carbon chain. So, for instance, here again is the Fischer projection for D-glucose. While it's easy to look at, it doesn't actually represent what happens to most glucose molecules in nature. You may remember from several sections ago that we learned about a very specific type of reversible chemical reaction that can occur when you place a carbonyl bond in close proximity to an OH group. Even more significantly, that particular type of reaction is favored if the carbonyl bond and the OH group are actually part of the same molecule. As a result of this particular reaction, we'll actually form a new link that bonds one end of the molecule to the other end. So rather than this open version of the molecule, where it exists as a relatively straight chain, the molecule will actually curl around and create a ring structure. What type of reaction are we talking about? Well, it's a hemiacetal formation, a carbonyl bond reacting with an OH group. So while glucose can exist in this open chain form, in this Fischer structure, if you will, it can also exist in a ring form. That ring form is what's known as cyclic glucose, in this case cyclic D-glucose. And the structure we draw is what's called a Haworth structure or a Haworth structure, depending on your pronunciation. The other thing that's important to remember about this is that this is not a one-way reaction. It actually goes both ways, and an equilibrium is established between the two molecules. In the case of glucose or other similar monosaccharides, the cyclic form is far more stable than the open chain form. So more than 99% of glucose molecules actually exist in a cyclic structure. It's important, though, to remember that there is a small fraction in the open chain form because that expands the number of chemical reactions that it could be part of. After all, the open chain glucose contains an aldehyde functional group, and we've learned about a large number of chemical reactions the aldehyde functional group can do. Now, it's important to be able to visualize how an open chain molecule will change into its cyclic form and vice versa, but it's not actually as intimidating as you might think. And in order to make this as easy as possible, what I want to do is walk you through the actual process that occurs, but I want to encourage you not to get bogged down in the details. The reason is, once you've seen how it occurs, I'm going to immediately show you a shortcut that means you won't have to visualize that whole process every time. I'm going to stick with D-glucose for this example. And you'll notice, if you can see it, that I've highlighted the carbonyl carbon at the top of the molecule and the OH group on the second to last carbon. This is where the reaction will take place between these two different parts of the structure. And the reason that it's that particular OH group, as opposed to any of the other OH groups on the molecule, is that this will allow the ring to have 6 members, or 6 atoms. 6-membered rings are much more stable than 4 or 7-membered rings, so those are the most common kind that we form. Although, you'll also occasionally see examples of 5-membered rings. I want you to mostly focus on these 6-membered rings, however, for our class. And I'm generally going to give you aldohexoses to keep things simple. The first thing you want to do to visualize how the open chain form is going to change into the cyclic form is to basically lay the open chain form down on its side. When you do that, be sure that you're not changing the position of any of the OHs. Notice that all the OHs that were pointing right on the original structure are still pointing down together. The OH that was pointing left on that original structure now is pointing up. Now, I want to imagine twisting this part of the structure around to form a ring. And it's almost as if the tail end of the molecule with the CH2OH is being pulled around the back of the molecule to meet up with the carbonyl carbon. So, I imagine that a ring is starting to form because I'm basically pulling the molecule around behind itself. In order to get the right structure, however, I need to put the carbonyl carbon close to the OH group that's highlighted here. To do that, I'm going to allow the single bond to rotate so that the OH is closer to the carbonyl carbon. And likewise, the single bond the carbonyl carbon is attached to also rotates to put them in close proximity. Here's where my hemiacetal reaction takes place. You may remember from our hemiacetal examples in a previous section, we learned that a new bond forms between the carbon and the oxygen of the alcohol, and a new bond forms between the oxygen and the hydrogen of the alcohol. Then I end up breaking apart the double bond into a single bond and completely breaking the bond between the O and the H. When I do that, I create this new hemiacetal structure and I completely close the ring together. Again, this is a reversible reaction, so it can go both ways. Now, like I said, if you can visualize that, that's useful, but it's not absolutely necessary to get the right final structure. If we know that we're going to form a 6-membered ring, we can be guaranteed that we're always going to get the same basic backbone, which is 5 carbons and an oxygen. Furthermore, Haworth structures are always drawn in the same orientation. So the oxygen is always on the top of the ring on the right-hand side. Furthermore, the carbon that was part of the aldehyde or ketone group is always located in the same position. Now here's how to do this very simply. Notice that in my final structure, I have some of the same OH groups while other OH groups have chemically reacted. Let's look at what happened to each carbon. My carbon number 1 was part of the carbonyl bond when I started this reaction, but at the end of the reaction, I no longer have a carbonyl bond. Instead, I have a new OH group attached to carbon 1, as well as a new connection between the carbon and the oxygen. We'll come back to this carbon in a second because it actually has some special significance. Let's go on though first and look at some of the other carbons. On carbon 2 in the original structure, I had an OH group that points down. Notice the OH group is still present in the cyclic form and it's still pointing down. So even if I hadn't completely visualized this whole process, just by keeping the OH in the same orientation, I'm assured I get the right structure. The same is true for carbon 3. In carbon 3 I had an OH group pointing up. Well, on the ring structure, my third carbon still has an OH group pointing up. And again, for the fourth carbon, the same thing is true. On the original structure, the OH pointed down, so on the cyclic structure, I ensure that the fourth carbon's OH group also points down. This brings me to my final chiral carbon, which is carbon number 5. Now, in this case, the OH group has actually been chemically reacted. It's not present anymore because it's part of the hemiacetal. So while the OH group pointed down when I was looking at the original structure, that OH group isn't present anymore. And also, I still have the CH2OH at the end, but it's pointing up from the rest of the ring. So, to summarize, on carbons 2, 3, and 4, I keep the OHs in the same arrangement. In this case, 2, 3, and 4 had OHs in the down, the up, and the down position, and I see that on my cyclic structure, again, they're in the down, the up, and the down position. On carbon 5, I'm not going to have any choice to make because there's a CH2OH that points up from the ring and the OH group has turned into an oxygen on the ring. Now back to carbon number 1. Carbon number 1 had been part of the carbonyl carbon, but it now contains an OH group. So does this OH group point up or down? Well, the answer is both. Carbon number 1 is what's called an anomeric carbon. An anomeric carbon is essentially one where the ring closed, and because of that I have a new OH group, and I can draw it pointing either up or down. Those are just two different versions of the same molecule. And there's a way to designate which one you're dealing with. If you happen to draw the OH pointing up, you're dealing with what's called the beta form of the molecule. If the OH points down, you're dealing with the alpha form. The technical term is to say that the alpha form and beta form of this cyclic glucose molecule are anomers of each other. It's somewhat related to the concept of isomers. Let's look at this in even more detail. So here's my structure with my anomeric carbon. Now the form that we'll see it drawn in many times is essentially this form with some fancier shading. The shading's just meant to demonstrate that you're looking at the molecule's cyclic structure from the side. It's supposed to make it easier to see up versus down in geometric arrangements. This particular version, whether you look at the version at the top of the screen or towards the bottom, has an OH group that points up. So would I call this the alpha form of D-glucose or the beta form? Well, in this case the OH points up, and when OH points up we're dealing with beta forms. So this would be beta D-glucose. I could just as easily have drawn alpha D-glucose by drawing the exact same structure and pointing the OH on the anomeric carbon down. That literally would be the only structural difference, and it would look like this. So again, beta D-glucose and alpha D-glucose are anomers of each other. And as long as we're dealing with a monosaccharide and nothing more complex, these are essentially reversible. Because again, the hemiacetal formation itself is reversible. So the glucose could unwind back into this open chain form, and then it could recoil into a cyclic structure, and you have a 50-50 chance of whether it forms the alpha or the beta version. Now I know you're anxious to try one of these. Again, I recommend sticking with the idea of just drawing the backbone of a cyclic structure and then transposing the OHs into the correct positions based on whatever your original open chain structure looked like. Let's try an example. Draw the cyclic alpha conformation of D-galactose, which I'll show you in a second. Remember, I recommend numbering your carbons to keep track of which OHs you're working with and what orientation they're in. Here's the structure of D-galactose. Again, not something you have to memorize, but take a minute, pause the video, and go ahead and draw the cyclic alpha conformation. To draw the most stable form of alpha D-galactose, I'm actually going to start by simply drawing the backbone that I know will exist. That backbone is going to be a 6-membered ring where one of the atoms involved is oxygen. So I always start by drawing this structure. Whether or not you choose to put fancy shading on your structures will have nothing to do with the grade you receive in this class. So if you want to try to look a little bit more sophisticated in your structures, you might draw some shading, but don't worry too much about it. Now, like I said, I recommend numbering your carbons to keep track of them. So here's carbon 1, 2, 3, 4, 5, and 6. And on this structure, those will correspond to 1, 2, 3, 4, 5, and 6 will be the carbon in the CH2OH group. If you got stumped earlier, now that you have this much of the structure, feel free to pause the video and start again. If you didn't, let's go on. The carbons that will remain the same in terms of containing an OH group with the same orientation are carbons 2, 3, and 4. Because I would think of this whole molecule as laying down on its side, this OH group on carbon 2 would point down, whereas the ones on carbon 3 and 4 would point up. So I'm going to show those on my structure by linking an OH to carbon 2 that points down and linking the ones on carbon 3 and carbon 4 to point up. I'm almost done with my structure now because I have all of my bonds accounted for with the exception of what's on carbon 1. One of the bonds on carbon 1 will go to a hydrogen, and the other one that I have to fill in will go to an OH group. Where they go, respectively, depends on what conformation I'm in. In this case, I asked for the alpha conformation, or the alpha anomer. The alpha conformation is the one in which OH points down. So because of that, I can imagine the OH pointing down and a hydrogen pointing up. This gives me the alpha D-galactose molecule. It's in its cyclic structure, which is the way it would most commonly exist in nature and in the human body. Be sure to do some practice problems with these, because I know they're of the particular type where they look a little bit overwhelming to begin with, but once you get the hang of them, you can actually do them very, very quickly. Furthermore, as I mentioned, I'm going to try to make things as simple as possible by really focusing on aldohexoses. So while there are other examples out there of pentoses and ketoses in general, I'm mostly going to do aldohexoses for our class. And that's because those are some of the most important ones to understand biochemically. Now let's talk a little bit about what we've seen now with monosaccharides. Even though monosaccharides are relatively simple, they're called simple sugars, and they are the simplest of the carbohydrates. They can exist in multiple structures. They exist in an open chain structure, which is not really favored, and they can exist in a cyclic form, which is far more favored at equilibrium. One of the difficulties when working with monosaccharides is that because both of these structures can exist, even though one is more common, they can both chemically react. So the open chain form with its aldehyde functional group can still chemically react like an aldehyde. That means it can be oxidized and it can be reduced. Meanwhile, the cyclic form can also react chemically. Not only can it unravel in a reverse hemiacetal reaction, it can also do its own types of chemical reactions. Most significantly, it can do a reaction to form an acetyl. And consequently, that means that monosaccharides can react to form larger saccharide structures that contain two or more monosaccharides brought together. If you have two monosaccharides combined together, you have what's called a disaccharide molecule, and if you combine three or more, we have polysaccharides. We'll be getting into disaccharides and polysaccharides as part of the next section. But we'll end our introduction to carbohydrates here now that we understand a little bit more about monosaccharides.